We continue our discussion of section 3.5. Today we will talk about applications of the fundamental theorem of arithmetic. Please take a look at theorem 6. We will not prove theorem 6. It's a hard to prove classical result. But let us look at what it says. Let a and b be relatively prime positive integers. So the greatest common divisor of a and b is 1. Then the arithmetic progression an plus b contains infinitely many primes. So let us discuss one trivial case of theorem 6. Let a be 2 and b be 1. Theorem 6 in particular says that there are infinitely many prime numbers of the form 2n plus 1. This is exactly what we have here. There are infinitely many prime numbers of the form 2n plus 1, where n is a positive integer. So we can easily prove a particular case of theorem 6 when a is equal to 2 and b is equal to 1. It is easy to prove this. To prove this result, we just note that there are infinitely many prime numbers and the only even prime number is 2. Since there are infinitely many prime numbers and the only even prime number is 2, the rest are odd prime numbers. There are infinitely many odd prime numbers. And we're done. Now let us discuss a significantly harder to prove particular case number 2. Here is example 2. Suppose a is 4, b is 3. There are infinitely many prime numbers of the form 4n plus 3, where n is a positive integer. In order to prove this result, first prove the following lemma. If a and b are integers, both of the form 4n plus 1, then their product is also of this form. Here's how we do it. Since a and b are both of the form 4n plus 1, there exist integers r and s such that a is equal to 4r plus 1 and b is equal to 4s plus 1. Therefore, a times b is equal to this. Now let us expand parentheses and factor out 4 here. Done. Observe that the expression inside parentheses is an integer number. Therefore, AB is of the form 4n plus 1 again. Now let us prove the main result. We will prove it by contradiction. Let us assume that there are only a finite number of primes of the form 4n plus 3. Let us list all these prime numbers. Let us denote the first prime number, which can be written as 4n plus 3 by p0. The first prime number of this form is, of course, 3. So p0 is 3, and then we have p1, p2, and so on, pr. All these numbers are prime numbers of the form 4n plus 3. Here is what we do next. Let us consider the following new number. 4 times P1, P2, and so on, PR, plus 3. Note that 3 is P0. So what is written here can be rewritten of the form 4 times P1, P2, and so on, PR, plus P0. Let us compare this number with the number that we used in order to prove that there are infinitely many prime numbers. Let us go back to one of our previous handouts over here. Folks, please take a look. Please compare this. And we used this construction in order to prove that there are infinitely many prime numbers. Compare this with this. Over here, we have the sum of two terms. Term number 2 is the number 1. Term number 1 is the product of all prime numbers. Of course, here we assume that there are finitely many prime numbers. Over here, we have a slightly different idea. We do not consider over here the product of all prime numbers of the form 4n plus 3. We consider the product of prime numbers starting from the second prime number. We do not include this one. So over here we start from P1. This is the second prime number of the form 4n plus 3. Then we multiply these by 4, and then we do not add 1 here. We add the first prime number of the form 4n plus 3. Why we need this construction? We will see it in a moment. But the point is, if we consider this, we will be able to get a contradiction. Note that we need a contradiction because we assume to the contrary that there are only a finite number of primes of this form. So consider this. Let us show that one of the prime factors of Q is of the form 4n plus 3. So once again, don't confuse factorization of Q and this expression. What we see over here is not factorization of Q. It's just some product. 4 times P1 times P2 and so on times PR. Now let us factor Q. Let us factor the whole thing. So over here we claim that one of the factors of Q is of the form 4n plus 3. Moreover, one of prime factors. Here is why. First of all, observe that any integer is either of the form 4n or 4n plus 1 or 4n plus 2 or 4n plus 3 by the division algorithm. So for any integer, there are only 4 possibilities. It is of the form 4n or 4n plus 1 or 4n plus 2 or 4n plus 3. Note that any factor of Q cannot be of the form 4n or 4n plus 2 because both 4n and 4n plus 2 are even numbers. But Q is odd because it is equal to even number plus odd number even number plus odd number is an odd number. So Q is odd. Therefore, Q does not have an even factor, because if Q has an even factor, Q is even, but Q is odd. So, conclusion, any factor of Q is either of the form 4n plus 1 or of the form 4n plus 3.
Could you repeat the last part if you don't mind?
So, since any integer can be either of the form 4n or 4n plus 1 or 4n plus 2 or 4n plus 3, and since Q is odd, for any factor of Q, there are only two possibilities. It is of the form 4n plus 1 or of the form 4n plus 3, because any factor of Q cannot be of the form 4n or 4n plus 2. Do you understand what I'm talking about?
Yes, thank you.
So, once again, any factor of Q is either of the form 4n plus 1 or of the form 4n plus 3. Let us prove that there is at least one prime in the factorization of Q of the form 4n plus 3. We will prove it by contradiction. Suppose there are no prime factors of Q of the form 4n plus 3. This means that all prime factors of Q are of the form 4n plus 1. But if any prime factor of Q is of the form 4n plus 1, by the lemma above, Q is of the form 4n plus 1. But Q is of the form 4n plus 3. And by the division algorithm, the remainder is unique. An integer cannot be of the form 4n plus 1 and 4n plus 3 simultaneously. Conclusion, there is at least one prime factor of Q of the form 4n plus 3.
Could you just explain briefly why Q cannot be in the form 4n plus 1?
Because it is of the form 4n plus 3. By the division algorithm, a remainder is unique. According to what is written here, we conclude that if we divide Q by 4, the remainder is 3. But if Q is of the form 4n plus 1, and we divide Q by 4, the remainder is 1. Does this make sense?
Yes, thanks.
Here is what we do next. So, at least one prime in the factorization of Q is of the form 4n plus 3. However, over here we have all prime numbers that are of the form 4n plus 3. So, according to what we just said, Q is divisible by at least one of the numbers from this list. Let us show that this is impossible. Here is why. First, let us show that Q is not divisible by 3. Here is how we do it. First, let us move 3 to the left. We will get the following. q minus 3 is equal to 4 times p1 times p2 and so on times pr. Now, if q is divisible by 3, q minus 3 is divisible by 3. Since the left-hand side is equal to the right-hand side is also divisible by 3. Cannot be. By the fundamental theorem of arithmetic, factorization is unique up to the order. But over here, there is no 3. This number does not have 3 in its factorization. We got a contradiction. Q minus 3 is divisible by 3. This is not divisible by 3. We get a contradiction. Similarly, suppose Q is divisible by one of these prime numbers. In this case, let us move this to the left. We will get this. Now, since some pj from this list divides q, and since pj is one of these numbers, pj divides the whole expression. But this expression is equal to 3. We get a contradiction. pj is bigger than 3 and pj divides 3. So if q is divisible by 3, we get a contradiction. If q is divisible by one of these numbers, we get a contradiction. So if we assume that there are only a finite number of primes, we get a contradiction. Folks, we are done with this example. Any questions?
Sorry, where does I understand, well, actually, no, I don't understand. The contradiction part, like at the end. Could you explain that again?
Yes. So over here, we say that q is divisible by one of these numbers. You agree with that?
Actually, wait.
Probably not. Okay. So please take a look. It's written at least one prime in the factorization of q is of the form 4n plus 3.
Oh, and that comes from the division algorithm, right?
No, give me a second.
Plus the
So
left.
we just proved that at least one prime in the factorization of q is of the form 4n plus 3. Do you understand why?
Yes.
Since over here we have all prime numbers of this form, q is divisible by one of these numbers. Agree?
No, I do agree.
You agree, correct?
Yes.
Now let us consider two cases. First, suppose that q is divisible by 3. We get a contradiction. Then let us suppose that q is divisible by one of these numbers. We get a contradiction. So on the one hand, q is divisible by at least one of these numbers. On the other hand, we show that if q is divisible by 3, we get a contradiction, and if q is divisible by one of these numbers, we get a contradiction. Therefore, what is written here is not true. Therefore, the opposite is true, means there are infinitely many prime numbers of the form 4n plus 3. How about that?
Yes, I understand now.
Any other questions?
Yeah, Professor,
Yes.
by doing this, haven't we proved that Q is also prime?
We do not prove that q is prime.
I'm more alluding to the result that we can calculate the next biggest prime by simple iteration then.
What do you mean by next biggest prime?
Because we have all of these forms P0 through PR of that are prime that are of form 4n plus 3, right?
Yes.
Then by this algorithm, we can say that we can just keep on plugging in these numbers into 4n plus 3 and keep on getting prime numbers.
What you are saying is actually not correct. Here is why. Note that we came up with the conclusion that Q is not divisible by any of these numbers thanks to the assumption that there are only a finite number of primes. Like, going back to this, Q is not divisible by any of these prime numbers, but it does not necessarily mean that this is prime. You see?
Okay, I see.
For example, okay, so yes, okay, here's an example. This is not a prime number.
Okay, cool.
Conclusion, this number is not necessarily prime.